Okay, we're going to look at this related rates problem, and what we have here is a pretty classic problem. It says we have a balloon, but we're going to pretend it's a perfectly spherical balloon. It's not going to be oblong or something that's not a perfectly round sphere. It's being inflated so that the radius is growing at a constant rate, and this word right here is important. It's a constant rate of 2 centimeters per second. And we're interested in how fast the area is growing when the radius is 5 and when the radius is 10. So when I do a related rates problem, I always try to identify my variables and my constants and any unknowns that I might want to find out. So let's try to identify all the variables first. And the first variable I run into is my radius, or r, that we'll refer to it as. And what do we know about the radius? Well, a lot of people want to go ahead and just plug this 5 and 10 in right away and say, well, the radius is constant because they see this number here. And actually, this number right here tells me that my radius is actually growing. Okay, that's the rate of change of the radius. In other words, dr dt, the rate of change of the radius with respect to the rate of change of time. Okay, and this is equal to 2 centimeters per second. Now this is where this notation of a derivative or a rate of change really makes sense, because up here you have this rate of change of the radius, okay, 2 centimeters. Centimeters is the linear unit on the radius, and then the rate of change of time, and the units on that is seconds. Okay, the area is the next variable that we have. We know that the area is getting bigger. I think everybody's blown up a balloon in their childhood, and they know that as you blow it up, the area gets bigger. Okay, so we're actually interested in the rate of change of the area. So the rate of change of the area with respect to the rate of change of time. And we have no idea what that is. That's what we're trying to figure out. Okay, so that's really step one, to identify the radius, or excuse me, to identify your variables, which are right here, and to identify your rates of change. Any constants involved in the problem. Here's our constant, and here's our unknown right here. This is what we're trying to solve for. Okay, the next step in a related rates problem, once you've identified all of your unknowns and your constants, is you try to relate your variables in an equation. Okay, and the equation that's going to relate the area and the radius is the area of a sphere. And the area of a sphere is 4 pi r squared. Okay, so this is the area, the surface area for a sphere. If you didn't remember that, you can look it up. And before I go any further with this, it turns out we don't really need to do this in this problem, but I always ask myself if I have too many variables. I know I'm going to be differentiating this, so I ask myself, let me just get a different color here. I ask myself, when I differentiate this, I know I'm going to get a dA dt when I differentiate that a. And that's a good thing, because that's what I'm trying to find. Now, a lot of people think that's a variable, but just remember that pi is a constant. And my other variable is r. So when I differentiate the right-hand side, I'm going to get a dr dt, and that's a good thing, because I know dr dt, it's 2. There are no other variables in here that I have to worry about. There's not going to be a weird dv dt that's going to be popping up that I don't know what to do with. So looks like we're good to go. So let's go ahead then, and we will go ahead and differentiate this thing. So the derivative of the left-hand side is dA dt, and the derivative of the right-hand side, now I'm just going to treat this as a constant right here, because it is a constant, and that derivative of the right-hand side is going to be the constant multiplied by the derivative of r squared. Well, the derivative of r squared, we have to use chain rule here. The derivative of r squared with respect to r is 2r, but the chain rule says that I have to come inside the r and take the derivative of it as well, and that is just dr dt. Okay, so there's our equation. Now, really the last thing to do is to, once we found the equation, once we differentiate the equation, now we can go ahead and substitute in what we know and solve for what we don't know. So what do we know? We know, what do we know? Well, I guess we know R, don't we? We know that we're interested in dA dt. This guy right here, we're interested in dA dt when R is 5. So let's go ahead and substitute a 5 in for R. Two times, here comes the substitution. I'll do the substitution so that you can see. There's the substitution. And then dr dt. What is dr dt? Dr dt from the above problem is 2. So the stuff in yellow here is the stuff I substituted. Now all that's left to do is to crunch this on your calculator. Now you can leave the pi in there. This isn't too hard to multiply. This will be 10. 10 times 4 is 40, times 2 is 80. So you would get 80 pi. Now think about the units on this. What would the units be? They would be centimeters squared per second, because we're talking about area now. Okay, now if you really wanted to make sense of this, because 80 pi, I don't know what 80 pi is. I could kind of imagine what it is, but it should be right around 251.2, and the units are the same, centimeters squared per second. Handwriting's terrible, I apologize. Okay, so there is dA dt right there. That is the rate of change of the area. Okay, now follow-up question is, well, what is the area doing? What is the area doing at when the radius is 10 centimeters? Well, you can see all I really need to do is come up here to this 5 and change it to a 10. And you could probably imagine what's going to happen. If that 5 got changed to a 10, what are you going to have instead? Well, let's just write over here, this is when the radius was 5. Well, what happens if the radius is 10? Well, you can go ahead and change that 5 to a 10, and you would get, what would you get? You get 20, get 160 pi, wouldn't you? You get 160 pi, okay, or approximately 502.4, 502.4, and the units on it are centimeters squared per second. Okay, there you go. So I guess the natural question would be, is the rate of change of the area, is it constant, is it increasing, or is it decreasing? And you can see that as time goes on, my area is growing at a faster and faster rate. In other words, there's some positive acceleration associated with this balloon blowing up, at least acceleration for the area. Okay, so in the next video we'll go ahead and look at the same problem, but we'll look at the volume instead.